I'd like to spend a few minutes going over these problems in Chapter 10. These are the homework problems that I just assigned the other day. So problem 1 is a pretty standard problem with a wheel spinning. They give you the final angular velocity, and in my problem it's 12.5 radians per second. Yours should be something close to that. They give you t or delta t. We'll just call it t. 3.07 seconds in my problem. And they tell you that the wheel starts from rest, so omega initial is equal to 0. And the object is to find the final velocity. No, we have the final velocity. The object is to find through how many radians the wheel traveled, okay, delta theta. So you can do that a couple of ways. First, you have to find the angular acceleration, okay? So you know omega final, you know omega initial, and find alpha, you know t. All right, I'm not going to do the calculation. It's pretty simple. It's 1D motion, just like we had in the past, where this was v final, this is v initial, and this is the acceleration. So once you have alpha, you can use omega final squared plus minus omega initial squared is equal to 2 alpha theta final minus theta initial, and this is delta theta. You can also use, since you know t and you know omega initial, you can also use theta final minus theta initial is equal to omega initial t plus alpha over 2 t squared. That's our 1D motion equation, just like we had before with 1D motion. I don't think you'll have any trouble with that. Number 2 is a repeat of number 1. It's a dentist drill. It starts from rest. And the only little, not tricky, but one of the little things that you have to do in problem 2 is they give you the angular speed in revs per minute. You need to convert that to radians per second. So there are 2 pi radians per rev. Okay, so that cancels the revs times 1 minute is equal to, you guessed it, 60 seconds. Okay, so you can convert this to radians per second, and then once you have that, that is the same problem as in number 1. I can't remember if that's omega final. I guess that's omega final is radians per second. It's the same as number 1. Number 3. So for number 3, it's a problem, a multi-part problem on finding the torque on an object. You have several forces acting at a lever arm on a wheel, and you're asked to find the torque. Just remember that counterclockwise torques are positive and clockwise torques are negative. You put your fingers of your right hand in the direction of the torque, okay? If it's counterclockwise, that's positive. That would be coming out of the board. Your thumb gives you the direction of the torque. If it's clockwise, that's a negative torque, and your thumb is into the board. Torque magnitude is RF sine phi. And the way I've defined it is, if this is R, this is R, and this is F, this angle is phi. Okay? It's the angle between R and F. Now, the only one that may give you a little bit of trouble on this problem, the only torque, is the one that they have at the top. I think they have a wheel like this, and then they have a little inner part, and there's a force acting at this point, and they give you an angle for the force. That angle is, I'll call that angle theta. I'm not sure what they call it, probably theta. Okay. So this distance, this would be R, and that's F, okay, and the angle theta. Now, the way the torque is defined, it's the angle between R and F. So let me redraw this little picture over here. Here's R, and here is F, and this is not to scale by any means. They give you this angle theta, okay? For the way I've defined it, this angle would be phi. All right? That way, a positive torque, a counterclockwise torque, which is positive, you get a positive answer for the sine of phi. So phi in this case is equal to 90 degrees plus theta. Okay? So that little angle's theta, that angle is phi. All right, you're going to get a positive answer for that because the sine, I think the problem that I have, this angle was 30 degrees. So you're going to get something that's 90 plus somewhere around 30, which will be 120 degrees. That's a positive torque, and that's what you need. Okay? So beware of that. Number 4. Number 4 is a disc, and they're including a torque. So once you figure out the acceleration based on the torque, you can just review what we did in problem 1 and problem 2 and solve that. Let me show you what I mean. Okay, so this is a disc. So the moment of inertia for a disc, a solid disc, is equal to mr squared over 2. It's a uniform disc, solid. That's the total mass. That's the radius of the disc squared divided by 2. I really wish we had time to calculate these moments of inertia. It's a lot of fun, or at least I think it's fun. Okay. So we know, they give you a torque, I think. We know that the torque is I alpha. That plays the role of the mass, that plays the role of the acceleration. That's the moment of inertia of the disk times the angular acceleration of the disk, and that equals the torque. So given the torque, you can solve for alpha. Alpha is equal to the torque over that moment of inertia. All right. Once you have that, then it's just like problem 1. Omega final is equal to omega initial plus alpha t. Okay. And you do have to convert, I think this is part A, you do have to convert revs per minute to radians per second. I showed you how to do that in problem 1. And then for part B, C1. Okay. See problem 1. All right. Number 5. Number 5 is several point masses along the y-axis, and you're asked to calculate the moment of inertia about the x-axis because that's the axis of rotation. So here's the x and y axis, and you've got several, I don't remember how they're distributed, but nevertheless you have several point masses distributed along the y-axis. And remember that the moment of inertia for point masses, you just sum them up. Sum over I of m sub I, r sub I squared. So r is that distance from the axis of rotation. So if this is m1, this is m2, this is m3, this distance would be r3, this is r1, and I'll draw that over there, that's r2. Okay? Sum it up. Find the moment of inertia about the x-axis. That's part A. In part B, find the kinetic energy. Well, kinetic energy, once you have that moment of inertia, the kinetic energy of rotation is 1/2 I omega squared. Okay, so I think they give you the angular velocity. You've just calculated the moment of inertia. You can find the kinetic energy. Then they ask for the velocity of each one of the little objects or the point masses. You can do that with V is equal to R omega. If you know the angular velocity and you know how far from the axis of rotation the point mass is, that's the tangential velocity. It's just R times omega. In part D, kind of just a little exercise, you find the kinetic energy from summing up all of these little velocities squared. You're summing up all the kinetic energies of the little point masses. And then you're asked, well, do B and D jive? Do they equal one another? And they do. I think there's a part in there where you have to upload some sort of document. I gave 0 points for that. If you click and look at the point value for each one, you'll see that that's 0 points. Number 6. So for number 6, this is almost identical to the example that I did the other day in class, which I posted on YouTube. You can look that up. This is a disc with a light string and a mass falling that's connected to the string. The first thing they ask you to do is to calculate the tension in the string. Okay, so let's do that. Number 6. So here's a disk. Here's an axis of rotation, which is at the center of the disk. That's nice. If the rotation were over here, that would be a little bit harder. Okay. The disk has a total mass m and radius r, and hanging from it is a mass m. That mass m is some distance h above the ground. So let's draw a free body diagram for the disk and for the hanging mass. For the disk, okay, we have the tension, and there is a support force. I'll just call it a normal force. I think it's some sort of axle through here, and then big mg. Okay. These two forces are not going to play a role in this problem. They're there. You have that support, some sort of support, and mg. These cancel. They're not providing any torque, so I'm not going to deal with these two forces. But we do have the tension force. All right? That tension force is providing a torque on the disk. For the hanging mass, little m, just like always, you have mg and then tension in this direction. So that tension force is producing a counterclockwise, this is that distance r, that would be our little vector. This angle is 90 degrees, it's coming right off the edge here, all right? So I'm gonna make this direction like I did the other day. I don't have to, we could do it differently, but I'm going to make that direction positive. This is a counterclockwise torque from our point of view, and that counterclockwise torque would be positive. So if I have a positive acceleration, then I have a positive angular acceleration, then I have a positive acceleration for the falling mass. Okay. Apply Newton's second law to both of these objects. So for the disk, okay, the torque is equal to RT. It is a positive torque, and that's equal to I. I'm not going to write I sub disk here. It's understood that it's the moment of inertia of the disk, which is big mr squared over 2. This is for the disk. For the hanging mass, we've done it 1,000 times. If down is positive, then we have mg minus t is equal to little m a. If we can find a relationship between a and alpha, we can combine these two equations and solve for t. What's that relationship? That relationship is that alpha times big R is equal to a. It's coming off the edge. The angular acceleration of a point at this point, okay, is R alpha. So alpha is equal to A over R. I'm going to use that here, and I'm going to combine these two equations and solve for t. So this equation, okay, let me just draw that. From the bottom equation, T is equal to mg minus ma. That's clear. All right. For this equation, substituting in for alpha, we have RT is equal to I alpha, which is A, over R. Okay? Now, combining those two, I'll leave some of the algebra up to you. We get that A is equal to, moving things around, we get that A is equal to R squared T over I. I don't want to get those T's and I's mixed up, but R squared T over I. Now substitute that back into here, and then we'll have an equation in just the masses, G and T. And you get T is equal to mg minus little m R squared T over I. I'll leave the algebra up to you to solve for T, move things around, solve for T, and once you have T, okay, plug it in, see if it's right. Then in part B, that was part A. In part B, they ask you for the acceleration of the falling mass. Well, you just calculated T here, use this equation, okay? If you have T, you can easily calculate A. You know, you might do part B first. Eliminate T and solve for A, and then solve for, it doesn't matter, all right? One is about as the same as the other, okay? Then in part C, they ask you for the final velocity of the falling mass when it hits the ground. All right? So, how will you do that? Well, you know A, you know delta Y, okay? That was H. You're using 1D motion, it's falling, you know the acceleration, you know the distance. Use 1D motion. Okay. You know the initial velocity. The initial velocity is 0. Starts from rest. I did want to mention, even though I don't think I didn't put any points for, you know, it's got one of those sections where you upload an explanation or something. I did want to think about this in terms, or just mention the energy consideration for this. How much energy is available, how much potential energy is available to the system? Little mgh. You have a tiny mass, it's h above the ground. That is the total potential energy available to the system. So you can use work energy where negative delta PE is equal to delta KE. However, you have to be careful. This is the change in kinetic energy of the falling mass and the disk. The kinetic energy goes both into the mass that's falling and the turning of the wheel or the disk. So it starts from rest. So mgh, that's the initial potential energy. I'll make the ground 0. That's equal to the change in kinetic energy. It starts from rest. So that's 1/2 m, that's little m, v final squared, plus 1/2 I of the disk, omega final squared. Okay? Then you can find the relationship between omega final and v final. I did an example problem like this the other day in class. So omega final is equal to v final over r. So omega final squared is equal to v final squared divided by r squared. All right. Then you can make a substitution for omega final squared because you're asked for the final velocity of the falling mass. So you get mgh is equal to 1/2 little m v final squared plus 1/2 I v final squared over r squared. And this would work, you know, if this were a disk or a hoop or whatever it is. In our special case, it's a disk. And you can make the substitution and solve this with energy. You have to do some algebra and find v final. It's analogous to what we did previously with energy, work energy, and falling objects. We were able to find that final velocity based on energy considerations, that work done by gravity, and that work going into the kinetic energy of the system. All right, so that's it for chapter 10. Let me know if you have any questions. I'm available. All right.